Hello, good afternoon everyone. So let's start today's session. So in today's session also we are going to further extend the concepts related to concurrency control. In the last class, we have gone through few important concepts related to the schedules, those are being produced. So we mentioned three important properties of the schedule. So we mentioned that schedule should be serializable, schedule should be recoverable, and it should be cascadeless. So cascading rollbacks should not be there. So all these three are the desirable properties for a schedule. We have gone through the concept of serializability, and also we have seen the test for serializability. So if there is a schedule and if we would like to check whether the schedule is serializable or not, then we have seen how to test it. So we may draw a graph, precedence graph, and we may have the arcs between the nodes. The nodes are actually the transactions, and if the transactions conflict with one another with respect to a particular data item, then we are having the arc between these two transactions. So if we create such kind of a precedence graph, and if the graph is acyclic, then and then only we say that the schedule is conflict serializable. If there exists a cycle in precedence graph, then we say that the schedule is not conflict serializable. So we have checked, or we have gone through that test for serializability. Now let us compare concurrency control and serializability tests. So testing a schedule for serializability, after it has executed is too late. What we mean by that? See, we have the schedule already created, and after creating the schedule, we are checking whether the schedule is serializable or not. Right? So this process is little late. Instead, what we can do, or what we should do, is we should develop a concurrency control protocol that will assure that whatever schedule is being produced, that is serializable. So instead of initially creating the schedule and then testing the schedule for its serializability, what needs to be done is we should go for concurrency control protocols, such that the protocols themselves create the schedules, those are serializable. So goal of concurrency control is to develop the protocols that will assure the serializability of the schedules. So they will generally not examine the precedence graph as it is created. Instead, the protocol will impose some kind of discipline that avoids non-serializable schedules. So some kind of discipline, some kind of protocol is being imposed such that the schedules, those are being generated in the system, those are serializable. Right? So this is the goal for concurrency control mechanisms. So tests for serializability in this situation help us to understand why a concurrency control protocol is correct. So only for validation. So I hope you must have understood the motive behind this concurrency control protocol. So concurrency control protocols are being designed such that they will impose some discipline that avoids the creation or generation of non-serializable schedules. Right? So let's proceed now. What kind of concurrency control protocols we are going to study? So we are going to study lock-based protocols. Then we'll be focusing upon timestamp based protocols, then validation based protocols, and the multiple granularity protocols. So under concurrency control, in fact, there are lots of different kinds of protocols, but in our curriculum, we are having these 4 kinds of protocols, those we are going to study, right? So let's begin with the log-based protocols. So what is the prerequisite for log-based protocols that we are going to discuss first? So if we are talking about some lock on some item, what it indicates, if we are locking the data item, it means that we are having the exclusive use of that data item. Right? So if one transaction is having the lock for a particular data item, then it means that that transaction is having the authority to use that data item. So if the data item is being locked by a particular transaction, meaning that transaction can use that data item. So lock guarantees exclusive use of a data item to a current transaction. So locks are required to prevent another transaction from reading the inconsistent data. So we have gone through few problems. In fact, more precisely 3 problems. If we are not having implemented the isolation, right? Then what are those problems? One of the problems is it may happen that if there are concurrently executing transactions, then it may happen that one transaction is being executing and the other transaction, if the proper care is not been taken, then other transaction may read the inconsistent data, intermediate inconsistent data of the transaction, right? But if we impose the locks, those may prevent another transaction from reading the inconsistent data. So that is one important usage of the lock. So most of the multi-user database management systems are actually automatically initiating and enforcing the locking procedures. Lock managers are there in database management systems. So those lock managers actually manage the information about the locks and they are responsible for assigning and policing the locks used by the transactions. So lock manager accept the request from the transaction for accessing a particular data item, and lock manager actually grants the permission to the transaction to use that particular data item, right? So let us see now various levels of lock granularity. So the data items can be locked at various levels. So what are those granularity levels? So locking can take place at different levels, maybe at database level, table level, page level, row level, or field or attribute level. So what we mean by all those levels for locking that we are going to see next, right? Now, let us assume that we are having the database level locking mechanism. Database level locking mechanism. So what we mean by that? So see here, we are having transaction T1, right? And transaction T1 wants to update the data element from, say, table A. So this transaction T1 requests the lock for the database, right? Because table A belongs to a database. Let us assume that we are having the payroll database. So this database is having many different tables. So we are having two transactions actually, transaction T1 and transaction T2, right? So initially this transaction T1 wants to update this table A, some element, some row from this table A. So T1 requests lock on entire database, right? Now the system will grant the request. So what will happen then? The lock on the entire database is provided or granted to this transaction T1. Okay, so entire database is now locked and transaction T1 may perform whatever are the updates on table A, right? But at the same time, transaction T2 is also requesting for a lock on the database because transaction T2 wants to update, say, table B, some element from table B. But as this is a database level locking mechanism, the entire database is locked, right? And the grant is with T1. So unless T1 unlocks the database, T2 cannot access any data element from the database, right? So even though T2 is requesting a lock on the database, T2 has to wait because the lock is with transaction T1. So T2 now waits for some time. So whenever T1 unlocks the entire database, then and then only our lock manager will allow this transaction T2 the lock for the database. So T1 has unlocked the database at this instance, and now the transaction T2 who was waiting for the database, right, is now granted the permission to access this database, right? So T2 is now having the lock on this database, and now further T2 may perform. Unless T2 unlocks the database, no other transaction can access the database, right? So this is the database level locking. So for whatever update the transaction wants to have, the entire database is being locked. So such kind of a mechanism is good for batch processing. But such kind of a database level locking mechanism is unsuitable for online multi-user database management systems. Because unless one transaction releases the lock, other transaction is not able to access the database. And this should not be the case if my database management system is multi-user, and that too many online users are working with that database management system. So this database level locking system is not good for multi-user database management systems, typically the online systems, right? So T1 and T2 cannot access the same database concurrently, even if they are using the different tables. In fact, T1 wants to use table A, T2 wants to use table B. But as we are having this database level locking mechanism, entire database gets locked, and even though T1 and T2 wants to deal with different tables, these two transactions are not having the access of the database concurrently, right? So this is the drawback of database level locking. So the next level of granularity is table level locking. So what we mean by that? See here, once again, we are having the same database, payroll database, and we are having this table A. So transaction 1 wants to update some row, say row 5, and there is one more transaction T2 who wants to update row 30 of the same table. Right? So T1 and T2 can access the same database concurrently only if they are using different tables. So if T1 wants to use table A and T2 wants to use, say, table B, then it is allowed to use this database concurrently. But if both the transactions want to use the same table, but they are updating different rows, but they are using the same table, then they are not allowed to work concurrently. So see here what happens is transaction T1 wants to update the row number 5 of table A and T1 is requesting lock on table A, entire table A. So the request is being accepted by the manager and the lock is being granted to T1. At the same time, T2 also wants to access the same table, but T2 wants to access another row. But still, as this is the table level locking mechanism, the entire table is being locked by T1. So T2 will not get access to this table. So T2 has to wait until T1 unlocks this particular table. So whenever T1 completes its execution, T1 can unlock this table and then only T2 can have the lock on this table A and then only T2 can proceed. So please remember, in table level locking mechanism, if two transactions are using different tables, then they are allowed to use. But if two transactions are using the or want to use the same table, then this concurrent access will not be provided. Right? So once again, such kinds of systems may not be suitable for multi-user database management systems, because many times it happens that more than one users actually want to access the same table. But in this situation, table level locking, if they want to access the same table, then one transaction may get the access, but other transactions need to wait. Right? So this is what table level granularity is. Is there any doubt so far? Yes? Is there any doubt? May I proceed?
Yes, ma'am.
Right. So the next level of granularity is page level lock. So what we mean by page level lock? As we know, the tables are spanning more than one disk blocks or pages. Right? So if we are talking about a table, a single table, as we are storing lots of data in a single table, to store one table, we may require more than one pages. So what is this page level lock? In page level locking, an entire page or a disk block is locked. I'll repeat. In page level locking, entire disk page or a disk block is locked. Right? So, what we mean by this? See once again, here we are having transaction T1 who wants to update row number 1. And this row number 1 of table A belongs to page 1. Okay? Transaction 2 wants to update rows 5 and 2. Right? So, in this case, transaction T2 wants to update this row 2 which belongs to page 1 and row 5 which belongs to page 2. So, in this scenario, as this is a page level locking, at a time one page is being locked. So, if transaction T1 wants to update row 1, then the system will accept the request, okay, and this page 1 where this row 1 is present, that page gets locked. Entire table is not being locked. Please remember, entire table is not being locked, but only this page or this disk block is being locked. So, the request is granted, this page is being locked. So, T1 performs whatever update that transaction wants to perform on this row 1. Okay, unless T1 completes and unlocks this page 1, this page 1 cannot be accessed by any other transaction. But at the same time, if transaction is requesting to access another page, then it is allowed. So, transaction wants to update row 5 and transaction 2 is requesting the lock for page number 2. So, if transaction 2 is requesting a lock on page 2, then as transaction T1 is working with page 1, this page 2 lock can be granted to transaction T2. Transaction T2 performs updation on this, say, row number 5 and then releases the lock, or may not release the lock, maybe, whatever may be the case. But whenever transaction T2 requests for page 2, it gets granted. But whenever T2 is now requesting for page 1 also, T2 has to wait because the lock is with transaction T1. After unlocking this page 1 by transaction T1, then and then only transaction T2 gets the access for page 1. So for this much amount of time, transaction T2 needs to wait. After releasing the lock on page 1 by T1, T2 is granted that lock, right? And afterwards, T2 may work with this row number 5. So after dealing with both the rows, transaction T2 may unlock both the pages, page 1 as well as page 2. Right? So, as here it is the page level locking mechanism, many of the transactions can access the same table if the data belongs to different pages. Right? So, such kind of a mechanism is most frequently used in multi-user database management systems. Page level locking is being used frequently in multi-user database management systems. So, let us go to the next level of granularity, and that is row level lock or row level granularity. So, see here, what is the case? concurrent transactions can access different rows of the same table, even if the rows are located on the same page. So we have reduced now the constraint. In the earlier case, the entire page was locked for a particular row. But now in row level locking mechanism, it is possible to access two different rows of the same table, even if the rows are on same page. Say for example, this transaction T1 wants to update row 1 and transaction T2 wants to update row 2. Row 1 and row 2 belong to same page. So what will happen? Both the transactions are granted the request. Why? Because one transaction wants to access row 1, another transaction wants to access row 2. So these two different rows are being accessed. So even though they belong to the same page, the respective transactions are being granted with those locks. Right? So if we go with this row level locking mechanism, then it improves the data availability. But to implement such kind of a mechanism, the database system needs to have lots of overheads. So every row must have a lock, and that lock needs to be read and written too. So obviously, to maintain such kind of a locking mechanism, the database system is having lots of overheads associated, right? So this is row level granularity. One level further, we may have the field level or attribute level granularity. So what we mean by that? So this level of granularity allows concurrent transactions to access even the same row as long as they want to access different attributes. Right? So now granularity is for the fields. So if I am having the fields like A, B, C, if one transaction wants to access attribute A from the same row is same. So transaction T1 wants to access attribute A from row 1 and transaction T2 wants to access, say, attribute C from the same row 1. Then under field level granularity, this is allowed. Right? So this kind of granularity is most flexible, but it requires extremely high level of overhead, extremely high, because it comes to the individual attributes. So lots of housekeeping need to be done, lots of bookkeeping needs to be done, and that is why the overheads associated are extremely high. Right? So I hope you must have understood all these levels of granularity. So let me continue with another concept, and that is a kind of lock that we may have. So we may have binary locks. So if we are having binary locks, meaning it is having only two states. Either the data item is locked, that means state 1, or the data item is not locked, meaning state is 0. So such kind of binary locks if we have, These eliminate the lost update problem that we have seen earlier. So the lock is not being released until the write statement is completed. So we cannot face the problem of lost update that we have seen earlier in case of binary locks. But the binary locks are considered too restrictive to yield the optimal level of concurrency. Because even though there are two read requests from two different transactions, so even though the transaction wants to read the data item, the transaction do not want to update anything, then also the data item gets locked. So even though there are no updates, even though the transaction only wants to read the data item gets locked in case of binary locking. And this reduces the concurrency in our system. And that is why we are having few more kinds of locks instead of going for binary locks. So we may have the exclusive lock or we may have the shared lock. So what we mean by exclusive lock? The access for a particular data item is reserved for the transaction who is locking that particular data item or that particular object. Right? So the exclusive lock must be used when the potential for conflict exists. So if there is a possibility of having the conflicts, then one should go for exclusive lock. So when there is a possibility of conflict, if one transaction is working on read and other transaction wants to write. So if one of the transactions wants to write the data item, then always there is a conflict. Right? So exclusive locks need to be used if there are such kinds of conflicts while reading or writing the data items. Right? So when a transaction wants to update a data item, meaning when a transaction wants to write a particular data item and no locks are currently held on that particular data item by another transaction, then the transaction is granted with exclusive lock. So exclusive lock is granted if and only if no other locks are held on the data item. I'll repeat, the exclusive lock is granted if and only if no other locks are held on the data item. Right? Now, let us see what we mean by shared lock. Concurrent transactions can be granted the read access simultaneously. So what we mean by that? If transaction T1 wants to read and if transaction T2 also wants to read the same data item, both are reading the data item, so they may acquire this shared lock because they are reading, not updating, not writing. Right? So the shared lock can be issued when a transaction wants to read the data and no exclusive lock is held on that data item. So multiple transactions can each have a shared lock on the same data item if they want to just read the data. But if one of the transactions is having exclusive lock on the data item, then the shared lock on that data item cannot be granted. Right? So, see here the mutual exclusive rule. Only one transaction at a time can own an exclusive lock on the same object or data item. So, with all these concepts, we are having a lock compatibility matrix. So, what is lock compatibility matrix, or what to infer out of this lock compatibility matrix? So, see here, suppose transaction T1 is having shared lock on data item Q, and transaction T2 wants to have the shared lock on the same data item Q. Then the status is true. What it means? If T1 is having shared lock and if T2 is also requesting for shared lock on the same data item, then it can be granted. True, it can be granted. Right? But if T1 is having exclusive lock for the data item, T1 is having exclusive lock for the data item, then if T2 wants to have shared lock or if T2 wants to have exclusive lock, then in both the cases, the access cannot be granted. So if the data item is locked by T1 with exclusive lock, then no other transaction can access that particular data item. Right? So, if one of the transactions is having the exclusive lock for the data item, then other transaction cannot access that data item. But if both the transactions are having shared lock, then that data item can be accessed by both of these transactions. Right? So, when to grant exclusive lock? If the data item is not having any other lock and if the transaction wants to write, then the exclusive lock needs to be requested and also granted. If both the transactions want to read only the data item, then there is no need to go for exclusive lock. But the transaction may request for shared lock. So, got the concept? What is exclusive lock and what is shared lock? Right. So, these kinds of locks can be used for the lock-based protocols. Or in other words, the lock-based protocols are based upon such kinds of locks. Right? But whenever we are allowing such kinds of locks, there are certain overheads associated with the database system. So what are those overheads? Obviously, the lock manager needs to know the type of the lock held on the data item. Unless and until the lock manager knows whether that data item is locked and what kind of lock is there, it is not possible to grant the permission to access that particular data item. So the type of lock held must be known before a lock can be granted. Okay. Also, there is some overhead associated with one mechanism wherein a lock can be upgraded from shared to exclusive, or it can be downgraded from exclusive to shared. So, in short, If we go with such kinds of lock-based methods, obviously some overhead is associated. And what that overhead is? The type of the lock held must be known before a lock can be granted. And secondly, if there is upgradation or downgradation of the lock, then obviously to follow this mechanism, some overhead is associated. Also, with lock-based methods, there are two possible problems. Those we may have. And what are those problems? The resulting transaction or the resulting schedule rather may not be serializable. So if we go with such kinds of locking mechanism, sometimes it may happen that the schedule is not serializable. Secondly, if we go with such kinds of locking mechanism, whatever schedules are created, these schedules may create deadlocks in the database. So these are the major problems, those we may face in case of these kinds of shared or exclusive locks. Right? So we are going to discuss these problems later at depth. So with this preliminary discussion, let us proceed with one example of locking. So see here, we are having this transaction T1 and we are having this transaction T2. So what this transaction T1 is doing? Transaction T1 is transferring amount 50 from account A or from B to A, from account B to A. Okay, and what this transaction T2 is doing? Transaction T2 is reading the balances of account A and B and simply displaying the sum. So these two are the transactions. Okay, so see here how we are going to provide the locks. As data item B and data item A both are being updated in this transaction, transaction T1 will ask for exclusive lock on B. So if transaction is having exclusive lock, then the transaction is having the sole access to that particular data item. So transaction T1 can read as well as write that data item. So T1 asks for exclusive lock on data item B, right? So once the T1 gets this exclusive lock on B, the data item B is read, then it is modified and then it is written back. After writing this, we may unlock this data item B because we are done with this data item. Now, what next? Transaction T1 asks for exclusive lock on data item A, then reads the data item, updates the data item, writes the data item, and then unlocks the data item A. Right? So these are the instructions from transaction T1. Now, what transaction T2 will have? T2 wants to read the balance A and B. So for reading, there is no need to have the exclusive lock. So T2 asks for shared lock on A, reads the data item A, and after reading, unlocks the data item A. Then T2 locks the data item B in shared mode then reads the data item and then unlocks it, and finally displays the result. Right? So these are two transactions, T1 and T2. Now, let us see one schedule that is being generated wherein these two transactions are participating, T1 and T2. Right? So see here how this schedule is being generated. So T1 is asking for exclusive lock on B. So we are having concurrency control manager. So this request for exclusive lock on B is sent to this concurrency control manager. So as there is no lock on this data item B earlier, concurrency control manager will grant the request. So grant exclusive lock on data item B, and this grant is for transaction T1. Okay, now what next? Transaction T1 is reading data item B, updating B, writing B, right? And once again unlocking the data item B. So this is a concurrent schedule. So few of the instructions from T1 and few of the instructions from T2 are interlinked. So after executing these many instructions from T1, T2 comes in and T2 asks for the shared lock on data item A. Now, data item A has not been locked earlier by any of the transactions. So obviously, concurrency control manager will grant the shared lock on data item A to transaction T2. So transaction T2 is now reading, then unlocking A, now requesting for shared lock on B. Now see here, T1 has unlocked this B. So now B is not having any lock with any of the transactions. So obviously, whenever this request comes in for shared mode locking on data item B, the concurrency control manager grants the permission to T2 for accessing this data element B. So T2 accesses this B and unlocks the B and displays the amount A plus B. Right? Now, see here. Now once again T1 comes in picture. So now T1 requests lock, exclusive lock on A because T1 wants to update A. So lock has been granted because there is no lock now, right now on data item A. So lock is granted. So T1 is reading A, updating A, writing A and unlocking A. Right? So this is how this schedule can work. But now please tell me whether this schedule is having any problem. Yes. Please tell me now whether this schedule is having any problem. Let us assume that initial balance of A is say 1000 and initial balance of B is say 2000. So please tell me if there is any problem with this schedule. Yes. Please work with this schedule. Assume these balances and go on computing and please check whether this schedule is producing the consistent state. Yes. Anybody please respond. Please be interactive. Yes. Whether this schedule is correct or whether there is a problem with this schedule. Yes, please pick up. Use these values and try to find out what is happening. Yes. What is the balance, initial balance of account B? What is the initial balance of account B?
2000.
So this is the first instruction in the schedule. So lock has been granted to T1 on B. So B is reading the balance of B. So what T1 is reading? T1 is reading the balance, na? Initial balance of account B. So what T1 is reading? What is the initial balance of B?
2000.
2000. T1 is reading 2000. What next? T1 is decrementing amount 50 from the balance. So B is being updated as B equal to B minus 50. And then T1 is writing B back. So T1 is writing B as 1950 in the database. Correct? And what is happening? Here itself, this transaction T1 is unlocking this data item B. As this transaction T1 has unlocked this data item B, meaning this data item B can be accessed by any other transaction. Right? Now, before transaction T1 goes for this instruction, what has happened? T2 has requested the lock for data item A that has been granted. So T2 is reading the balance A. So what is the balance of A?
1000.
1000. So T2 is reading 1000. Now T2 is unlocking A. No issues. Now T2 wants to lock B. As T1 has unlocked B, T2 can be granted with lock of B. So the lock is being granted. So now T2 is reading B. So what is the balance that is being read by B by T2?
1950.
1950, yes. After reading this balance, T2 is unlocking B and displaying A plus B. So what T2 is actually displaying? 2950. Right? What is actually sum of these two accounts? 3000. And consistency requirement is also 3000. So after executing this transaction, the system should have the balance 3000. So prior to execution of this transaction, the system should have 3000 balance. After execution of this transaction, system should have balance 3000. After and before executing of this transaction, the system should have balance 3000. Right? But what has happened here is, see, later on, once again, the schedule continues. The schedule reads the value A as 1000, updates A as 1050. So individually, if we look at this transaction T1, this transaction is correct. But whenever we look at this concurrent schedule, whenever we are having here T1 and T2, those are working concurrently. What has happened? T1 has unlocked this data item B too early. As a consequence, T2 has read this data item B, which is actually the inconsistent state. Right? So what's wrong with this schedule actually? Transaction T1 unlocked data item B too early, as a result of which T2 saw an inconsistent state of the database, and T2 has read some intermediate value. Right? So this schedule is not actually correct, because actually this schedule T2 is producing the summation of A and B, which is actually incorrect, because it is based on some intermediate value, inconsistent value that is being read by T2. And why this has happened? Because this data item is released or unlocked too early by T1. Right? So this is the problem with this example. Right? Now, what we can do, see here. We are having now two transactions, T3 and T4. Once again, transaction T3 is transferring amount 50 from B to A, and this transaction T4 is doing the same task, that of T2. So T4 is reading the balances of A and B and displaying the sum. But see here, what will happen now? Here, exclusive lock on B, reading B, updating B, then exclusive lock on A, reading A, updating A, and at the end unlocking of B as well as A. So even though transaction T4 comes in and asks for the shared lock on data item A or B, as these two data items are exclusively locked by T3, unless these data items are unlocked, this transaction will not get access of these two data items A and B. So if in this manner, if the transaction is organized in this manner with lock and unlock statements, then the schedule may properly work. Because here we are not releasing the lock early, but the lock is being released at the end after writing both the data items. So no other transaction will read the inconsistent state of the database, intermediate state of the database. And that is why this kind of schedule, if we have these two transactions in the schedule, then this schedule will work well. Right? So I hope you must have understood this concept. So here what has happened? Unlocking of the data item is delayed to the end of the transaction. And that is why this particular schedule having these two transactions would work correctly. Right? So I hope you must have understood the use of exclusive lock and shared lock. And if at improper place, if the lock has been released, then what happens? So you must have understood this. Any doubts so far?
No, ma'am.
Right. So let's go to the drawback of such kind of a locking mechanism. Right? So see here, we are having one schedule, schedule 2. Two transactions are participating, T3 and T4. So see what is happening. T3 is requesting exclusive lock. Right? Now, T3 is granted the lock. T3 is reading the data item, T3 is updating the data item and writing it back. So as we have seen, we have delayed the unlock for B. Right? We have delayed the unlock for B. Why? Because in earlier situation, when we have released that lock earlier, we faced the problem. And we do not want to face once again this problem. So what we have done, we are not unlocking this data item B until end. Right? So we have written this B. Meanwhile, what has happened? T4 appeared in the system and T4 is asking for shared locks. T4 wants to read data item A. So T4 wants to have the shared lock on data item A. So that has been granted. So T4 has read the data item A. That is fine. Now T4 wants to lock data item B in shared mode. Okay. Now what is happening here? Exclusive lock on data item B is with T3 and T4 is asking for shared. So if the data item is earlier having exclusive lock, then this transaction will not get any kind of lock. Right? So T4 will not be granted with lock on B. So T4 needs to wait unless this lock is released. But T4 is now waiting for transaction T3 to release the lock on B. But T3 is not releasing that lock. Instead, T3 wants to have the exclusive lock on A. Now, if T3 wants to have exclusive lock on A, T3 will not be granted that lock because the shared lock is there on A. So, exclusive lock and shared lock, those are not compatible. Only S and S are compatible. Right? So, one is having X, one is having S, another wants to have X lock, then these two are incompatible locks, shared and exclusive. So, the system will not grant exclusive lock on data item A. So, what will happen? This T3 also wait to have that access. Right? So, T4 is waiting for T3 to release the lock. T3 is waiting for T4 to release the lock. So, in this situation, neither T3 nor T4 can make progress. Why? Because they are waiting for one another. Are you getting me? You must have seen similar kind of situation in your operating systems, wherein the resources are being locked by the processes. Right? So, what we call this situation is called as, yes, what has happened here? T3 is waiting for T4 to release the lock. T4 is also waiting for T3 to release the lock. So no one is making any kind of progress. So this situation is called as, please pick up. You have gone through similar kind of concept.
Deadlock.
Yes, deadlock. So there is a deadlock in the system. So such kind of a situation is called as deadlock. Right? So in lock-based protocols, we may have the deadlocks. So to handle this deadlock, what needs to be done? Either T3 or T4 needs to be rolled back so that the respective locks are released, and then one may make progress. Right? So in locking systems, we may face the problem of deadlocks. Right? Now, let us proceed how to handle these deadlocks. I'm not going into the details right now, but these are the common methods, those you might have studied in operating systems as well. So, how to handle deadlocks? We may have the prevention policies, we may have the detection policies, and we may have the avoidance policies. Right? So, a transaction requesting a new lock is aborted if there is the possibility that a deadlock can occur. So this is what we mean by prevention. A transaction requesting a new lock is aborted if there is the possibility that a deadlock can occur. Right? Now, what happens in detection? The database system periodically tests the database for deadlocks. And if a deadlock is found, one of the transactions is picked up as the victim, and that transaction is being aborted. So that transaction gets rolled back. And once again, the same transaction which is rolled back, that may restart afterwards. Right? So in detection system, periodically the database management system checks whether there exists a deadlock, and if the deadlock is being detected, then one of the transactions is picked up as the victim and that transaction is being aborted. So once that transaction is being aborted, all the data items locked by that transaction are released, and then the other transaction may continue. So this is what we mean by detection. What is avoidance? In deadlock avoidance, the transaction must obtain all the locks those are needed before it starts its execution. So the deadlock is being avoided. Whatever are the locks, those are required for execution of the transaction. The transaction obtains all those locks, and then only the transaction starts working. So this technique actually avoids the deadlock. Right? So these are three methods to handle the deadlocks. I'm not going into the details of these methods because you know these methods. So you have learned these methods with respect to operating system, and the similar kinds of methods are there for databases. Okay, so how to select the deadlock control method? So choice of deadlock control method depends on the database environment. So what we mean by that? See, for example, if probability of deadlocks is low, then we may go with detection policies. If the probability of deadlocks is high, then we should go with prevention policies. If response time is not high on the system priority list, What does this mean? This means that we are not bothered about the response time of the system. Because if we go with avoidance, the response time may increase. Right? So, if we are not bothered about the response time of the system, then we may go with avoidance techniques. So, these are few guidelines when to choose which kind of deadlock handling mechanism. I hope you must have understood this. If you have any doubt, please let me know. Any doubt?
No, ma'am.
Right.